So our first big concept for this chapter is discussing pressure and how we measure pressure and the units that we use to express pressure measurements. Being able to measure pressure is essential to accurately determining how much of a gas we have, because we're going to see, given a constant volume and temperature, the pressure of a gas sample will increase with the number of moles. So, assuming we know the volume of a container in which a gas is stored and we know the temperature at which it's stored at, we can use the amount of pressure a gas exerts to determine how many moles of a gas we have. And in order to figure out that relationship, first we need to talk about what is pressure and how could pressure reflect the number of moles of a gas. So remember that for our ideal gas and our real world gases, gases mathematically are considered to consist of gas particles, which are either the molecules or the atoms, the smallest representative chemical chunk of the gas, in constant motion. So you think of a gas as particles in constant motion. Each of the particles have a kinetic energy, and they're widely spaced apart. So samples of gases, unlike solids or liquids, are mostly empty space. They consist of particles in high-speed random motion, which are constantly colliding with each other and constantly colliding with the walls of their container. So that's what we're showing in the diagram here. We have this rectangular container with gas particles in motion, and every time the gas particles collide with one another or collide with the walls of their container, they're exerting a force. So how can pressure reflect the number of moles of gas particles in a sample? Well, pressure is a measure of force exerted over an area. So every time you have a collision, gas particle on gas particle, or gas particle on the walls of the container, that collision exerts a force. A gas particle is very small, so the area over which that force is exerted is approximately the same area as the particle of the gas itself. And therefore, you have a force, you have an impact where a force is delivered over a very specific area, and that is a pressure. So mathematically, we express the quantity of pressure with a capital P, force with a capital F, and area with a capital A. The more force is exerted over a smaller area, the higher the pressure is. And so in kind of a macro scale, everyday world picture, remember that kind of in our real world, force is equivalent to weight. Weight is an example of a force, and an area would be an area of the ground over which that weight is being distributed. So for instance, if you look at an elephant is a very heavy mammal. When it steps, it exerts a force with every step. The force of that step is distributed across the entire pad of the elephant's foot. And so even though the elephant is a massive animal, it has a very big footprint, and the force of every step is exerted across the area of its foot. So as a result, even though the elephant is very heavy, the pressure of each step is not as great as you might expect. Your book goes through a calculation of exactly how much force a typical elephant exerts with every step. If instead you have much less weight, but you reduce the amount of the person or the animal that's in contact with a surface, you're delivering that lower force, but over a much smaller area. So for instance, another example that your book brings up is that a figure skater obviously weighs a lot less than an elephant, but when a figure skater is skating, their skate blade is the only piece of them that's in contact with the ice, and even then it's not all of the blade. So a figure skater actually would exert more pressure skating at any given point on ice than an elephant would simply walking on the ice, because the force of the figure skater, the weight of the figure skater, is being delivered over a very small area. It's just the point of the skate that's in contact with the ice. So pressure is not just force, it's force delivered over an area. And this is why very small particles that are in constant high-speed motion can exert such large pressures. In kind of our everyday lives, we often think of pressures as associated with inner tubes, either on car tires or bike tires, And in our everyday world, in the imperial system, pressure is typically measured in pounds per square inch. And if you think about pounds as a unit of force, square inches is a type of area, so the unit PSI, pounds per square inch, is a good representation of what a pressure is, force exerted over an area. And when you have pressure in an inner tube, that's a classic case of the pressure that you're measuring in the inner tube is due to the collisions of all the gas molecules inside the inner tube, pinging off the walls in the inner tube and exerting that pressure. And so the more gas you put in the inner tube, the higher the pressure becomes. And this is why we can use pressure as an indirect measurement and eventually a direct measurement of how many moles of gas are in a given container. Now, the SI unit of pressure is called the Pascal, capital P little a. 1 Pascal is equal to 1 Newton per meter squared. And Pascal is an excellent measurement of force if you're interested in physics or hardcore physical chemistry because it allows you to relate the pressure exerted by a gas to more fundamental properties related to force and area. But in general, a Pascal is not a particularly useful way of measuring pressure in the real world because it's such a small unit of pressure. And before we talk about some other units of pressure, let's talk about how we actually measure pressure. There's two devices that are used to measure pressure, the barometer and the manometer. A barometer is used to measure the pressure that the gases in the atmosphere are exerting, what we call atmospheric pressure or ambient pressure. And the way that works is a barometer traditionally was composed of a dish of mercury, and then there was a large column, a large glass column that the mercury could flow up or down. And the idea is that the atmospheric pressure would push on the pool of mercury in the dish, and the higher the atmospheric pressure, the more the mercury would be compressed, and the farther up the tube the mercury would rise. And so it became natural to measure the pressure of the atmosphere, not in pascals, but in the distance that the mercury would rise up this tube. So as a result, pressure started to be measured in inches of mercury or centimeters or millimeters of mercury, depending on where you lived and whether you used imperial or metric measurements. And the idea was that through a barometer, the pressure of the atmosphere was simply measured by how high up this tube the mercury would rise, and that gave you your pressure measurement based on the height of the mercury. Technically, the measurement is a little more complicated than that, and your book goes into this measurement in a little bit of detail because the pressure actually is reflected in how wide the tube is, the density of the mercury, and several other variables. But because everyone began to make their manometers to the same dimensions, we could reduce the pressure measurement to simply how high the mercury rose up the tube. So a barometer is still used widely to measure atmospheric pressure, although it's no longer necessarily done with mercury. You can also do this measurement with water or alcohol. You just have to have a pure liquid that you know the density of to make an effective measurement of pressure. There's another device that's used to measure the pressure of a gas in a laboratory setting where you have a captured gas in a vial. And this is a device known as a manometer. Manometer comes in many different forms, both open-ended and closed-ended, but the idea is a manometer, unlike a barometer, is designed to measure the pressure of a gas sample that has been collected in a vial. And so manometer is a name for a device that looks like a unit of distance or length, kind of looks like nanometer, but is actually just a device to measure pressure. A manometer works very similarly to a barometer, but it's set up to measure the pressure of a chemical gas sample. The idea is your gas sample is held in a vial with a stopcock right here. A stopcock is something that you probably used in some of your laboratory glassware before, and it's a simple Teflon or glass plug that's used to open and close a channel. It's like a faucet on a sink or any type of pipe. The idea is initially you have your gas sample in the vial over here on the left. You open the stopcock and that allows the gas to flow out into the manometer. When the gas flows into the manometer, it pushes on a mercury reservoir and it raises the height of the mercury on the right-hand side of the manometer by a height h. And so again, while the overall pressure that the gas is exerting is equal to the height that the mercury is raised times the density of the mercury times the gravitational acceleration constant pulling down on the mercury, because the density of mercury and the gravity on Earth are constant, we can get a pressure measurement that's simply based on how high the mercury rose. And this is why you see a lot of experimental measurements of pressure in either centimeters or millimeters of mercury. And as a result, even though the Pascal is kind of the most fundamental measurement of pressure, and in many ways it's the most physics applicable measurement of pressure, the Pascal is such a tiny unit of pressure that we rarely use it in chemistry measurements. Instead, we make our measurements in millimeters of mercury because that's easiest to measure and record based on a measurement with a barometer or a manometer, or we make it in atmospheres. And the conversion between atmospheres, millimeters of mercury, and pascals is something we'll practice quite a bit at the end of this first section. But 1 atmosphere is the same as 760 millimeters of mercury, which is the same as 101,325 pascals. So pascals are such tiny units of pressure that they're not really useful in experimental measurements of gases anywhere near sea level or at an elevation that people live. And so in general, when you're in the lab making a measurement of pressure on a gas, you'll see the experimental measurement made in millimeters of mercury. And later on, when we use the ideal gas law, we're going to see that atmospheres is the most effective unit of pressure to use if you want to relate the pressure of a gas sample to the number of moles within it. So generally, the way this is going to work is we're going to see problems where atmospheric pressures or gas phase sample pressures are measured in millimeters of mercury. We're going to convert them to atmospheres if we want to use them. So you don't need to worry about memorizing these conversions yet. They'll always be provided to you on quizzes and exams. But the way you get from one pressure measurement to another is to use dimensional analysis like you would when converting any other measurements, which is something that we're going to work on quite a bit today. There are several other units that are used to measure the pressure of a gas. These include torr, T-O-R-R, and a torr is equivalent to 1 millimeter of mercury. They're just two names for the same measurement. And you also have bar. 1 bar of pressure is nearly equivalent to 1 atmosphere of pressure, but it's a little bit less. 1 bar is exactly 100,000 pascals. So it's very close to an atmosphere, but is slightly smaller. And so the next thing we want to move on to today is some varied practice and do some example problems and let you self-practice or self-test on converting a measurement in one pressure unit to another pressure unit. I'll see you there in a minute.